Hello everyone and welcome back. My name is Mr. Kowalt, and in this video I'm going to show how to calculate the change of a buffer when you add an acid or strong acid or base to it. It's pretty simple. The first step you're going to want to do is you want to do a stoichiometry step where you calculate how much of the either strong base or strong acid reacts with either your base or your acid in the buffer. So you've got to kind of calculate that out to do an acid-base neutralization reaction. So so here's the information we're given. We're given 1 liter of buffer with 0.100 moles of the acetic acid and 0.100 moles of your acetate ion here. The Ka value for acetic acid is 1.8 times 10 to the negative 5. Because we have equal amounts of, or equal concentrations of your acid and its conjugate base, then in that case the pH is equal to the pKa, which is just the negative log of this, and that's 4.74. Okay, so that's the setup. That's what you are given and what you need to calculate. And then you're told you add 0.010 moles of solid sodium hydroxide to your buffer. Okay, so we want to calculate what the pH change of that is going to be. And then what we're going to do is we're going to compare that to what would be the pH change if you added the same amount of NaOH to pure water. Okay, so first thing we want to do is do a table where we're going to do the neutralization. So we got to do the neutralization first. So the neutralization, we're adding a strong base, and so we have our acid HC2H3O2 aqueous plus we have a strong base. We'll just write hydroxide because that's what's going to react, and that's going to then react with this, and it's going to form water, H2O liquid, plus we're going to form some C2H3O2 minus aqueous. Okay, so we were originally given, so we're going to have to draw a table that's kind of like the ice table, but this is before adding the base, and then this is adding the base, and then after adding the base. So before adding, after adding the base, or do the same thing if it's a strong acid. So here we got a strong base. So before we added the concentrate, the number of moles we had is 0.100 moles. And then before we added, there's 0 or approximately 0. And then we're ignoring the water. And then before we added the base, we had the same number of moles of the base. So 0.100 moles. So what are we adding now? So we're not adding anything here. So we're not adding this. We're adding hydroxide. So we're adding the base. So we're adding 0.01. So 0.010 moles of the base, and we're not really adding anything here. So then what's going to happen is this this is going to react to form, it's going to react with the acid. So 0.010 moles is going to react with the acid that we had to begin with, right? So this, it's a strong base, so 100% of this is going to react with an equivalent amount of this. So 0.01 is going to react with 0.01 of the acid. So when that happens, it's going to subtract out that amount. So 0.011 is going to be 0.090. Okay, so then that's going to be moles of the acid left. But then when it reacts, it's going to form the same amount over here. So you're going to have to add on this side as well. So then after adding, this is going to be gone, so it fully reacts. That's 0. And then you lose 0.010 moles over here, but you gain the same amount over here. So this would be 0.110 moles of your base. So now we have what after adding the base. Now we have what our initial amounts are of our conjugate base, our acid and its conjugate base. Now we can use this to do our ice chart. So let's go ahead and erase this. I'll be right back. Okay, so now we're back with our ice chart. And so here we have our acid reacting with the water, forming the hydronium ion and the conjugate base. And so we have our ice chart. So the initial conditions after we added the strong base is that now we have 0.090 moles here, so we don't need to write the moles. And then here we have 0.110, and then this is essentially 0. And so this is our starting, our concentration or starting amounts in the buffer. And so now we can do our change in equilibrium. So here we'll have a minus x here, since everything is 1:1:1 ratio. This is going to be a plus x, and this is going to be a plus x. And then we add everything together to get our equilibrium expressions, 0.090 minus x. And then this is going to be plus x, and this is going to be 0.110 plus x. And then we put this into our Ka value. So Ka is equal to 1.8 times 10 to the negative 5. That's going to be equal to the hydronium ion concentration multiplied by the C2H3O2 concentration, acetate ion concentration, and that's going to be over the acetic acid. So HC2H3O2 concentration, and then we just plug in the values or the expressions for the equilibrium. So 1.8 times 10 to the negative 5 is going to be equal to, these two are multiplied together, x times 0.110 plus x over this here, that's going to be 0.090 minus x. And then we can do our x is too small approximation. So here, this will go to 0, this will go to 0. And so now we can divide these and then solve for x. And when we do that, x is equal to x is equal to 1.47 times 10 to the negative 5. So x is equal to 1.47 times 10 to the negative 5. So we'll only allow 2 sig figs here because we have 2 sig figs here. And this is equal to our H3O plus concentration, which is what we have for x here. And so we can use this to find the pH. So all we need to do is take the negative log of this, but let's check the validity. So if we check the validity, we can divide this by the original amount of the acid here. So the original amount was 0.090. Multiply that by 100 and you get 0.016%. So you get 0.016%, less than 5. The x is too small approximation is valid. Okay, so then all we have to do now is take this x value, which is our hydronium concentration, and take the negative log of that. So we take the negative log of 1.47 times 10 to the negative 5, and that will give us the pH. And when we calculate that out, we get the pH of 4.83. So 4.83 is the pH after you've added the strong base. Okay. So the next thing you want to do is check it for water as well as pure water. Okay. So with pure water, we took 0.010 moles of the base and we put it into 1 liter of water. So what would be the molarity of that? So you do 0.010 moles in 1 liter of water and you get 0.010 molar NaOH solution, and you would plug that into your equation, take the negative log of that, right? So if you take the negative log of this, you'd get a pOH of 2, right? So then this gives you a pOH equal to 2, and you remember that the pH plus the pOH is equal to 14. So subtract 2 from 14 and you get the pH is equal to 12. So that's what the pH would be if it was just pure water. And here the pH is 4.83. So a big difference. So buffers are really helpful. One of the other things you could do is you can use the Henderson-Hasselbalch equation. So here's the equation right here. pH is equal to pKa plus the log of the concentration of the base over the concentration of the acid. So we know the pKa is 4.74. Oops. 4.74. And then plus the log of that, if we calculate that, that becomes plus 0.087. And when you add that together, you get 4.83, the same as you got there. So it works that way as well. So I hope you enjoyed this video. I hope it was helpful. If you like my videos, like, share, subscribe, hit the notification bell, put a comment in the comment section. Thanks for joining. See you next time.